So what you do here is you assume that there exists two distinct points. Oh yeah, and the question is, hold on, let me get the question in there. Tell for me, can someone describe for me, based on this diagram, what's the domain? Which part of this picture is the domain?
The blob.
The blob. Thank you. The blob is the domain. Why is it the domain?
It contains all the points.
What points?
In the
This
function.
table connects all the points in the function. What do you mean by that specific language? The domain of a function is what?
Set about points that are inputted into the function.
The input set. Yeah, the function is acting upon all of the sets, all of the points inside that blob, right? Okay, so it's taking that point xy and mapping it to what?
Axis.
On that graph, what is it mapping it to? What is xy mapped to? Let's follow the line here. Xy gets mapped to the f of xy. That's correct. So you have your input coordinate and you have your output coordinate. The function is taking everything that's inside that set and moving it over there. You usually have dealt with functions where you input a value and you get out a value. We now have functions where you're going to input 2 or more variables and output 1. Input 2 or more and output 1. So, yes? So you're plugging in 3 for x and 2 for y. So that's pretty straightforward. What about the domain? What about the domain? Now, the domain, instead of being on a number line, your domain is going to be on the what?
Plane.
On the xy plane. So on this first one, what's one thing you know? So for, well, I guess we'll start with this. F of 3, 2 on the first one is going to be the square root of
6.
over 2. Great. Now, if we want to figure out the domain, we have to figure out what are the things we need to avoid, which is delving into the imaginary land of imaginary numbers, which is the very real world, but I need to be careful about. So we know that x plus y plus 1 has to be greater than or equal to what? 0. So we know that x plus y has to be greater than or equal to...
-1.
That's one way to say it, sure. And you also know that x minus cannot equal... So x cannot equal 1. So one way you could say this is xy such that x does not equal 1 and x plus y is greater than or equal to -1. So that would be a set notation, but what's one other way you could write it?
Draw it.
You could draw it. You could draw it, exactly right. So if you draw this, x plus y is greater than or equal to -1. So that means that y is greater than or equal to what? Negative x minus 1. Negative x minus 1 looks something like... Will the line be dotted or solid?
Solid.
Solid because it's equal, right? And how do you figure out which side to shade? Well, pick of values. Is 0, 0 part of this? 0, 0 is a part of it, so what are we shading? Above the line. And then you want where x does not equal what?
1.
X does not equal 1. So then you could say, you could shade it in and then erase that like one dotted area, right? So no. So our input set it needs to be limited to this region in order to abide by, we don't like dividing by 0 and we don't want to take the roots of, the even roots of negative numbers. Yes?
Is there any new...
Since you're super duper amazing calculus students, you should be able to graph that. Y squared is greater than x.
Yeah, you just change it like this.
Yeah, so this is a parabola facing which way?
That right.
To the right, yeah. It's a parabola facing to the right, going through the origin. So you have this parabola going like this. Yay. And then how do you figure out if you shade the inside or the outside? Oh, first of all, it's dotted, right? Yeah, what should you plug in? 1, 0. Thank you for picking something nice. I'm always confused when people pick weird numbers. You can pick anything you want, right? So it's dotted.
Root of 54.
When x is 1, is that less than 0? If I plug in 1 for x, is 1 less than 0? 1 is less than 0?
Of course.
Wow, you guys are really going for the gold here. So we need to not shade the inside, we need to shade the outside. So finding the domain should be relatively straightforward. And to answer your question, no, there is nothing new. Yes?
How would we...
Okay, what happens, look what's going on here. As the wind speed increases, the actual temperature goes down. So what is this? This is modeled wind chill, exactly, right? So if I said the wind speed was 40, sorry, the velocity, yeah, the wind was 40 right here, so this column, and the temperature was negative 25. When wind is blowing, does it seem hotter or colder? It seems what? Colder, right? So when it's very cold outside and there's a lot of wind, you have to be very careful because it makes it feel a lot colder. It's like, so the actual temperature is what the air temperature is. This is what it feels like. So, for example, if I said 40 and negative 25, it actually is going to be negative 41. So this is a table for a 2-input, 1-output function. A 2-input, 1-output function. Vermont's last theorem. So you asked the question, here's the strong end of applied math, actuarial sciences. Pure math, here's the other end of it. Vermont made a statement in his notebook like 425 years ago where he put this out there and he said that if all of these values are integers, positive integers, there are no solutions for n greater than 2. He made that. So, you know, you can explain that problem to just about everybody because everybody in high school math, 3 squared plus 4 squared is 5 squared. 5 squared plus 12 squared is 13 squared. There's lots of Pythagorean triples, but if you change the power to 3 or higher, he said that there are no integer solutions. He wrote that down in the margin of one of his notebooks and said there isn't space for me to write the proof here, and then he died. For 400 years, people looked for a proof, and you know what? They never found one. So the common belief is that he really didn't have a proof, or if he did, he was wrong. About 10 years ago, a guy named Andrew Weil came up with a proof for this. It's like 200 pages long. There's like 50 people in the world that understand it, but it's rigorous. It's agreed upon to be a proof. That being said, what are people still looking for?
Simpler proof.
So maybe something simpler, right? This is about as pure as it gets. What's really cool about this guy's proof is not that he proved it, which is still really cool. It was a Millennium problem. He got like $1 million for it.
Did he get a Nobel Prize for it?
There was a Fields Medal. He did get a Fields Medal for it, as far as I know, which is the Nobel Prize for math. He linked all sorts of different. There's these different fields of math that I can't even begin to explain because I don't understand them. But he created these bridges. So his work that goes into the proof, he discovered a lot of new things along the way. This is about as pure as it gets. I mean, what's the direct practice? I mean, I can go up to just about anybody on the street and explain what this problem is asking, right? People could test it. They could come to believe maybe it isn't true. You know, they could come to believe something, right? If I ask them what's the practical application of this, the direct practical application, I don't know. But in the process of discovering this proof, he came up with all these different connections. And another way to look at it is if you only investigate things with immediate practical applications, we wouldn't be human. That's like the antithesis of what it means to be human. We are curious. We want to understand our universe. And if we didn't have that drive, we would be nowhere. We would be nowhere. And there's all sorts of things that major discoveries that were discovered in the process of trying to do something totally unrelated. Totally unrelated. Okay, so here's a 2-variable function, pumps out 1. Find me the domain and range of that function. Go. Do it now, by yourself. Theoretically, you should end up with something like, you have your axes. You should end up with something kind of like, whee. Something like this, right?
Yeah, it's half of a sphere.
It's half of a sphere, exactly. Great. It's half of a sphere. Now here's the question. Now, this is, these are lines I'm drawing so that you can see what it looks like, but that's another way you can draw this. You can set output values. If you set output values, so if I said this function is equal to 3, what are x and y have to be? If I set this thing equal to 3,
0, 0.
has to be the point
0, 0.
0, 0, right. Exactly. If I were to set this equal to, I don't know, let's say 2, like this, 9 minus x squared minus y squared, that is where does that equation intersect the plane z equals 2? And when you do it out, it comes out to 4 is equal to 9 minus x squared minus y squared, right? So that's x squared plus y squared is equal to 5. So it's a circle with a radius root 5, which is less than 3 but greater than 0, right? The point is you can draw out these traces. You can draw out these traces by picking output values. You actually have seen maps like this. If I just took these lines right here and flattened them, if I took this thing, here's the shape, ready? I drew those lines around it and I looked at it straight from above, what would you see?
Circles.
Okay, you would see circles. What type of map are you looking at? Topographical map.
There we go.
This bottom map. Each bottom map is spaced out. Listen, each bottom layer here, each of these lines represents 5 more feet of elevation. If the lines are closer together, what does that mean about the ground you're going to be walking on? It's going to be steeper, right? Because you know it just went up 5, but the lateral was smaller, so it's getting steeper. Topographical maps are exactly what we're looking at here. We just kind of popped it up. We popped it up and just graphed it in 3 dimensions. Why do we have to force it to 2? Well, maps need to be rollable. estimate the values of f13 and f4. How would you do that?
Find the point.
Find the point and then see how high it is. Exactly, right? So f13 is right here. It looks like it's between 70 and 80, but it's close. Well, hold on. It looks like it's a little closer to 70 than it is to 80, right? So I don't know, like, looks like, I don't know, around 73, right? And what about f45 here? f45 is right about here. It's between 50 and 60, maybe a little bit closer to 60, so maybe what? 56. So reading a topo map, you know, this is not an exact science right here because it's not super fine, but the idea is, what would this look like?
Oops. I mean, like things popping. I mean,
What would the graph look like? It would be like
two things
up
popping
and then one
up.
thing in the middle. It'd be like this.
Yeah, it was recording. Good, Chen. That was great. Okay, awesome. Record. So for example, we just had, what was it? It was SQ, I think it's let's see here. SQRT of, ready? 9 minus x squared minus y squared, like that. Then you hit plot. Look what it did.
That was fast.
Why does it have to-
I'm sure there's a way to make this bigger. Oh, there it is. Look. Because it's really steep. Because it's like when your calculator, the dots aren't actually there. So there's the x and y. But is this a great way to graph these surfaces? Absolutely. This is a great way to graph these surfaces. You want to know what you think look like anymore? There you go. So anyway, you can try this out. It's a great program. Use it. I think it's really cool. X, Y, Z is equal to x squared plus y squared plus z squared. How would you make a visual representation of that? What would you do? Yeah.
Wait,
It'd be like a sphere, like growing.
Okay, so you could use movement, right? You could use movement. You could show it as you change the output value. What's another way you could show it? Well, I'll give you a hint. Take a look at this picture. What could you do?
You draw that.
You actually see things like this all the time.
Is that like a solid thing?
You could make it a solid. You could bore out the solid, and then you could give each layer a different
Label.
or color, which is another way of saying label, right? So one way you can think about this is, let's say I had a contour map of a mountain, and then I measured the temperature at each point on the mountain, right? You can think of each space having a certain temperature, and that could be another representation of that last output. It's kind of weird, right? Point is, am I really going to have you graph things like this? No, I'm not. But you could do it with motion. You could do it with color. You could do it with straight out labels. But you need some other piece of information at each layer. So instead of each slice being like a narrow band, each slice in this case is what? A surface. Each slice in this case is a surface. Yes?
That, my question was, what happens if you had W